Next up, we have a second section on vehicles. This time I talk about submarines. The reason why I put this here is in the light of the idea of inspiring to you with simulation approaches and modeling approaches. So what is the scenario I want to address here? And this is basically the scenario I want to show you. Yeah. Why is it not? Why is it not running? So basically, it's a resurfacing. Yeah. So I click here through this one of a submarine, so breaking through ice. Yeah. So this is the scenario here, and what you want to make sure is that the submarine structure is strong enough to sustain breaking through the ice. And the main concern is not like structure modeling. I mean, this is something most finite element codes can easily do. The problem is how you model the ice. Yeah. And this is like I said, this is an inspirational idea how to model the ice. And this is what my colleagues came up with. So basically what you do is you breaking the ice modeling down into two sections. So there's like the regular section, which is just classical finite element approach. And then there's a part which kind of predefines the area where the ice flow or the ice can break. And when you do this is kind of taking this one and you're breaking it down into two parts. Yeah. So one part is modeled with finite elements. So you can see here, this block goes in here, it's modeled with finite elements. And the other part is then you're going to tie these elements are not connected on the nodes. So that these are just loose finite elements. However, you're going to tie them together by using so-called cohesive elements. Yeah. And then you're going to assign a cohesive element a certain failure criteria. Yeah. And what you can do with this one, you're combining, it gives the possibility to model cracks. Yeah. So you kind of have so-called macro cracks, which are the big ones, which are driven by the element length. So basically, the failure criterion of the element edge or in between the elements in between for pieces of elements, you're having the large cracks, and to kind of represent the small cracks happening inside of an element. These are usually micro cracks. You're going to kind of degrade the stiffness of the material. That means you're going to combine what we call then the cohesive element method with homogenization. Yeah, so this is where the name coming from. And my colleagues call this a whole method, but to be honest, this is just a modeling approach. To my opinion, it's not a method in its own. It's just how you can model this. Yeah. So the idea is microcracks you model by degrading the stiffness of an element. So the more microcracks you have, you accumulate the microcracks, the softer it becomes. Yeah. And at some point it will kind of be deleted because it completely fails based on microcracks, or you have macrocracks which are kind of modeled by cohesive elements in between. Yeah, you will get the PDFs afterwards. Here's a link to a PDF where my colleagues describe this approach in more detail. Yeah, but it's a really nice approach. So, and if you run a simulation, so this is basically a submarine breaking the ice, and yeah, this is how it looks like. Now you can see the strong deformation. You can also see the failure, and then the important part here again is it's not exactly how well or to model exactly how the ice is breaking. It's just you need to create some structure or some load on the structure based on your physical model or based on your reality with breaking ice. Yeah, so you're kind of finding a replacement model of the breaking ice in order to get a proper representation of the load onto the structure. And I think this is a very nice and a creative idea to do so.